For this problem, we will be using coordinate transformations into some uv values that we have already previously shown you in order to solve for a double integral. And in doing so, we're going to make our bounds easier. So right now our bounds are functions. And in the end, if you plug these in, you are not going to get some constant value. You could probably do it, but it will be significantly harder rather than just using coordinate transformations. And the coordinate transformations are already giving it to you. So our x value is equal to u over v plus 2, and our y value is equal to u times v over v plus 2. And this is analogous to saying x is equal to r cosine for the familiar polar coordinates, and r is equal to sine theta. And our job is to try to pick a transformation or pick bounds that makes it easy for us to integrate. And how do we make it easier for us to integrate? We'll have constants as bound. So hopefully at the end, we're going to get some double integral of our new function, right? F of u and v now, our new function, and maybe our bounds are 1 and 0 or 1 and 2. So we're trying to look for constants here. Let's actually draw out these graphs first for you to show you actually how hard it would be to actually integrate this. So this red line would be drawn out like so. And this green function, oops, wait, redo that. This green function will be drawn out like so as well. Something that looks approximately to this. Why did the color change? Something that looks approximately like this for the green function, and for our y is equal to x, just traditional slope line of 1. And lastly, let's pick, I don't know, blue. So a line with slope 2. Maybe something that looks like this. And our area of integration is something that just what the world is at, right? Let's shade it in. How could you possibly integrate this? Well, we're going to make it significantly easier for you by using the coordinate transformations given already. And sometimes problems will give you a coordinate transformation beforehand. And sometimes you have to make up your own, and I'll teach you how to do that as well. Actually, we can undo everything instead of erasing. Okay. You know what? I could have just erased there. So, first thing we're going to do, always find some Jacobian first. Maybe not always. But that's what I like to do because I can just get it out the way. So, don't forget about finding the Jacobian. It's pretty important. So we'll set up our Jacobian matrix. And remember, the matrix is set up like so, with rows designated to rectangular coordinates and columns designated to our new variables, u and v in this case. Sorry, v. Delta y, delta u, and delta y, delta v. If we find our u partial with respect to x here, this would be 1 over v plus 2. If we find our v partial with respect to with our function x, sorry, not with respect to anything, it would be negative u over v plus 2 squared. Our u partial for our function y is v over v plus 2, and we use quotient rule for this last one. And you get something that looks along the lines of this. Minus uv over v plus 2 squared. And in order to solve for the Jacobian, or our transformation factor, we got to find the determinant of this. First, let's just simplify this because it looks like an absolute monstrosity right now. You can simplify it with some algebra into 2u over v plus 2 squared. Okay, now let's solve for the determinant. So we multiply this guy right here, so across. And when you multiply that, you get 2u over v plus 2 cubed. And next, we subtract and we multiply it with the other cross. So if we subtract that and we multiply them together, we get uv over v plus 2 cubed. And then again, the negatives cancel out, so these just add into each other. And then we get 2u plus uv over v plus 2 cubed. And again, you can also factor out u, so you get 2 plus v over v plus 2 cubed. And a factor of v plus 2 cancels out since these have the same things inside, I guess same function inside of the parentheses. So you get u over v plus 2 squared due to the fact that we can cancel these out as our Jacobian. And let's save that for now. Up top. Now the order in which you do things truly doesn't matter. Let's put lines around this. The order in which you find a Jacobian or replace variables doesn't matter. But the next thing we want to do is find our bounds for our new variables. How will you do that? Well, there's already a very strong hint to setting u equal to 2x plus y. And the reason being is because these two functions are bounded by some constant number. And if we set u equal to 2x plus y, our old bounds look something like this. And our new bound is simply just replaced with u. And this is a u. Let's actually make this more clear rather than looking like a 4. So all we did was substitute u into here, because essentially these are equivalent. So our bounds for u are 4 and 8. And that was just due to the hint of this right here. Now keep in mind, once you find your values for u and v, you really need to watch out, because what if your values for u and v don't match up with your old functions? Meaning that if you plug in values for u, if you substitute all the values for u and all the values for v, and they don't give back just a constant y or x, not the constant, but the variables y or x for their corresponding functions, then you did something wrong. That's an easy check, and I'll actually show you that after this. So v is likely going to be dependent on something related to y's slope. Due to the fact that this has a slope of 1, this has a slope of 2, we can actually set up our v value to be equal to y over x. And this is sort of something that measures the slope. Therefore, the bounds for v will be determined by the slope, y over x. So originally we had, let's see, this is y over x. If you divide, so let me show you what my thought process is here. Divide by x on both sides, you get y over x is equal to 1. Correct? So this is our first bound. If you divide by, on the second function, y is equal to 2x with x on both sides, you get y over x is equal to 2. So our bounds currently for this function, if we algebraically manipulate them slightly, is y over x greater than or less than equal to 2. Bounded by 2 and 1. And if we substitute our old value here, v, into this, we simply get constants as our bounds for v. And now here's the tricky part. You need to test this out. So if you got these wrong, if you got your values for u and v wrong, or your bounds for u and v wrong, a very strong hint will be for this right here, using these functions right here. And the reason being is because you can actually plug in the values for u here. So let's actually set this. X is equal to 2x plus y. And I actually just substituted in for u here. And v is equal to y over x. So if we do v is equal to y over x plus 2, what do we get? Well, what we can do here is actually divide by x on both sides of this problem. And we divide by x, you just multiply by the reciprocal of whatever you're dividing by. And this is the reciprocal. If you multiply by x down here, you get x divided by x, which is equal to 1 on the left side of the equal sign. And you also get multiplied by 1 over x, correct? If you divide by x on both sides. You also multiply by x at the bottom here. And if you multiply by x, this denominator cancels out. And you get x multiplied by 2, which is equal to 2x. And these, since these equations are equivalent, all this does is simplify to 1. Therefore, this function is equal to x right here when you substitute u and v. So therefore, you know that you got the correct u and v values, and your bounds are right. So it's actually useful to do that. Maybe if you're, you feel like you're doing something wrong and you want a sanity test, that is a good way to know that you're on the right track. So now that we have our bounds, what can we do? Well, let's rewrite the double integral. And our bounds for u are 4 and 8, and our bounds for v are 2, 1, and 2. But first, we need to substitute the x and y values in our old function of f. So multiply 2 times x. So x is u over v plus 2. So if I substitute x with the values of our new transformation, you get this. Plus y. And y is simply just this transformation value here. We can then put this in our integral and then multiply it by our Jacobian. du dv, because that's the order in which we integrate, in order to solve for this function. But first, we need to just do a little bit more simplification. Let's erase our old things here. And this is just a simple double integral that you can actually solve with a little bit of algebraic manipulation. You can factor out, actually, let's show this first. It's just green. I like that color more. Red looks like ominous. Okay, we can add these two fractions together because the denominators are the same. You get v plus 2. We can factor out u to get 2 plus v, and we get v plus 2 down here. These cancel out because they are factors, and then we get left off with u. So this entire thing is actually equal to u. So if we rewrite our double integral, you get u times u over v plus 2 squared du dv. These are differentials that state the order in which we integrate. Drag this up into the corner. And to simplify this a little bit further, you get 1 over 2. The u multiplies into this fraction, so you get u squared over v plus 2 squared du dv. Simple double integral now. We can actually solve for this. Let's go ahead and solve for this. 4 from 8. And I'm not actually just ignoring, this other integral sign. I'm just going to omit it for now, just to make our notation clear. and we're integrating with this with respect to u. If you integrate this with respect to u, you get u cubed over 3v plus 2 squared, and our bounds are from 4 to 8 of u. If you plug in for 8, you get 512 over 3v plus 2 squared minus 64 3v plus 2 squared. Simplify this further, and you get 448. 448 over 3v plus 2 squared. So this will be treated as our new integrand. And let's actually integrate this now for v. So our bounds for v are 1 and 2. And our new integrand is just written down like so. 448 over 3 times v plus 2 squared dv. Once you integrate this, you'll get negative 448 over 3 v plus 2. And our bounds for v are 1 and 2. This looks like a delta symbol. I'm going to change this as 2. Bounds for v. All we have to do is just plug everything in, and once you simplify everything, you get 102 over 9. So this right here, let's use green because that signifies that you did it right. So this right here, 112 over 9, is our value for our integral using transformations. Let's move on to the next question. So for this problem, you are not given the transformation. So I'm not telling you what x and y are equal to. For this one, you're going to have to figure that out. And hopefully, your teachers aren't going to give you extraordinarily difficult problems to figure out, because this one, it's not that bad once I actually tell you and once you get some practice in. So for this problem, first I'm going to find a value for you. Remember, these transformations are very flexible. You can choose a lot of functions, and some of them may make it extremely hard or difficult, and some of them will make it very easy. So this is the one that a textbook told me, technically. But the transformation for u is equal to x minus y, because it would just make it extremely easy to integrate this if this was just the square root of u. If the integrand was just the square root of u, it would be extremely easy to integrate. It's just a single variable. And also, v is equal to y. And the reason being is because we need the values for x and y in order to find the Jacobian. So we can actually isolate x here to get x is equal to u plus y. So these equations are equivalent. But what we can actually do is substitute the value for y as v, because v is equal to y. So we can actually set this equal to x is equal to u plus v. And y is simply just equal to v. So let's go ahead and solve for our Jacobian. So the Jacobian matrix is set up like so. So delta x, delta u, delta x, delta v, delta y, delta u, and delta y, delta v. And as consistency goes, make sure your rows are designated for the same variable and your columns are designated for also the same variable, or whatever you're actually integrating with respect to is designated for your columns. So if we find the, I keep clicking Control X. If we find the u partial for x, it's just simply 1. If we find the v partial for x, it's just 1. If we find the y partial, the u partial for our function of y, it's just 1. 0, actually, sorry. Because our function y is not dependent on u. And if we find the v partial for our function y, it's just 1. And our Jacobian just ends up being 1 times 1. So we multiply these, you get 1 times 1, which is just 1. And 1 times 0 is just 0. So our Jacobian is 1 minus 0, which is equal to 1. Therefore, our Jacobian is equal to 1. I'm just going to keep it in the top for consistency sake, because you'll have to do that for every single problem. Okay, now that we have the Jacobian, what do we do next? Well, here's the tricky part, because you can't just directly substitute v into y here. Remember, these guys right here are a function of x. So our current bounds for this problem are y is less than or equal to x, and y plus 6 is less than or equal to x. So what does this look like with some more mathy notation? The bounds for x in this little hooky guy is, yeah, you know what? I'm not using crazy math notation. I'm just going to make this a lot easier for you guys. Our bounds for x is this. So what do we do with x in order to turn it into u? Well, in order to set x equal to u, we just subtracted by y. So if you subtract by y in all these inequalities, you get y minus y, x minus y, and y plus 6 minus y. So all we did was subtract by y through every inequality. And now this part right here, the center of our two-sided inequality, is equal to u now. It's actually a lot easier now that we have the bounds for u. So if you subtract by y here, you get 0. Y minus y is just 0. And if we substitute for u, x minus y is equal to u, so you get u. If we subtract by y, here you also just get 6. So these just two cancel out. So our bounds for u are 0 and 6. That was quite easy. And our bounds for v are even easier because, well, v is just equal to y. So our current bounds for y are 0 and 2, given by our order of integration and the bounds on the second integral. And we could just substitute y directly with v. So our v bounds are still 0 and 2. So 0 and 2 goes up to here. And we can actually rewrite this integral now. So if we rewrite this double integral, you get 0 and 6, 0 and 2, square root of x minus y. X minus y is equivalent to u, so we can actually substitute u into here. And we're integrating with respect to u first and then v second. And don't forget, we need to multiply by our Jacobian, but our Jacobian is just 1, so if we multiply by 1 with the square root of u, it just stays the same. And all this is just a simple double integral that in technically rectangular coordinates that you all are familiar with. So 0 to 6, integral of square root of u du is equal to 2 over 3 u to the power of 3 over 2. And our bounds are 0 and 6 for this. If we plug in for 6, we get, square root of 216 times 2/3. Simplify this further, and you get, what is this? Simplify this further, you get 12 over square root of 6 over 3, which is equal to 4 square root of 6. And now this is our new integrand. And our new integrand is simply a constant. So we just multiply it by v technically. So 4 times square root of 6 times v is equal to these bounds. Our bounds are actually 2 and v, sorry. 2 and 0. If you plug in for 2 here, you get 8 square root of 6. Plug in for 0, you just get 0. So 8 square root of 6 is our answer. Hopefully that was helpful. If you guys have any questions, put it down in the comment section.